Welcome students to a continuation of chapter 25, which focuses on the urinary system. We left off talking about filtration by the glomerulus. We're going to talk a little bit in this lecture just about kind of how we regulate how fast what we call the GFR, or the glomerular filtration rate, and that affects all kinds of things like our blood volume and extracellular concentrations and so on and so forth. A separate lecture will focus on reabsorption and secretion, and then a separate lecture on kind of regulation of the kind of concentration of the urine, and then a separate lecture for how the body kind of stores and transports the urine once it's made by the kidneys. But we left off talking about GFR, about the filtration, about all these different pressures that affect how much filtrate gets made. Of course, the biggest contributing factor is this very high pressure capillary bed in the glomerulus, again, fed and drained by two arterioles. Afferent arteriole leading in has a much wider diameter than the efferent arteriole leading out. That creates a very, very high pressure gradient inside the glomerular capillaries. So that's this hydrostatic pressure in the capillaries, the pressure of the fluid, kind of pushing things out of the capillaries and into the capsular space. We also have fluid in the capsular space, the filtrate that's being made. That pushes back against the glomerular capillaries, but it's a much smaller hydrostatic pressure than the hydrostatic pressure of the fluid in the capillary itself. Because of the filtration slits in the filtration membrane, big, large, clunky proteins, they remain in the blood. They don't make it out into the filtrate, or they shouldn't make it out into the filtrate. That creates an osmotic pressure inside the capillary, which is kind of pulling fluid and proteins, or fluid and ions, back into the glomerulus, back into the capillary, back into the blood. And if we sum our inward forces and subtract them from our outward force, we get a net positive filtration. So filtration is happening. That is what you want your glomerulus to be doing, filtration all the time. The rate at which that happens is known as the GFR, or the glomerular filtration rate. It is literally the volume of filtrate formed per minute by both kidneys. Normally that's about 100 to 125 milliliters a minute. Anything less, particularly if it gets less than like 30 or 35 or I think 15, that indicates kidney failure and indicates that there is something wrong with your kidneys and you want to take care of them. So GFR is affected by three things. The net filtration pressure, which of course is the biggest kind of contributing factor there. Again, the largest factor is the hydrostatic pressure. But also the surface area available. So if the filtration membrane were damaged, and made larger or shorter, that would directly affect GFR. And then the permeability of that filtration membrane. The glomerulus is a fenestrated capillary bed, so it's more permeable than, say, a capillary bed in a muscle or something like that. And if the filtration membrane, again, were damaged in some way or made more permeable, that would lead to increases in GFR. But maintaining this kind of normal GFR, that roughly 120 to 125 mils per minute, it's really important in terms of maintaining homeostasis for your body, because GFR affects blood volume, right? How much volume of fluid you have in your circulatory system, that affects your blood pressure. And if your blood pressure gets all sorts of wacky, that affects how your heart works, and it kind of snowballs from there. And so it's really important that the kidneys are properly doing their job. If GFR goes up, right, that we have more filtration happening, greater amounts of urine being made, that then decreases our blood pressure. If GFR goes down, that means we have less urine being made, which would increase our blood volume and increase our blood pressure. And so by kind of regulating GFR, it helps us regulate our blood pressure. So there are kind of two sets of controls in terms of filtration. There's intrinsic autoregulatory stuff, just like there is for capillaries elsewhere in the body. And then there's the extrinsic stuff that's mostly a function of the nervous and the endocrine systems. They have slightly different goals. The autoregulation by the kidneys, the intrinsic part of this, the goal of these mechanisms, we're going to talk about two of them. We call the myogenic mechanism and the tubuloglomerular feedback mechanism. These use the JGC. Their goal really is to make sure and maintain that constant GFR. And that's really what they're concerned with, is just maintaining GFR. Now, the extrinsic goals are the nervous and the endocrine systems influencing the kidneys to maintain blood pressure. And the nervous system and the endocrine system are more concerned with maintaining blood pressure than maintaining proper functioning of your kidneys. So if we're between 80 and 180 millimeters of mercury blood pressure, if we're in a relatively normal blood pressure range, then the kidneys will mostly be governed by these intrinsic mechanisms. But if blood pressure gets too high or too low, the extrinsic mechanisms, the nervous system, the endocrine system, will take over to get the blood pressure back into a normal range, kind of no matter what happens to the kidney. And at that point, when blood pressure is too high or too low, maintaining that blood pressure and getting it back to normal is actually more important than maintaining the proper functioning of your kidneys. So we're going to talk about the myogenic mechanism first. Myo means muscle, and so we're particularly talking about the smooth muscle that is in the walls of the afferent arteriole leading into the glomerulus. If your blood pressure goes up, that stretches the muscle in the walls of the afferent arteriole because it's being kind of pushed against more by a higher pressure. That leads the arterioles to constrict, which then slows the flow of blood into the glomerulus. This maintains the kind of ability of the glomerulus to function, even if blood pressure gets a little high. You're not kind of overwhelming the glomerulus in terms of this incredibly high flow that's just going in there and just busting it all open. It keeps it very similar to what we want it to be. And that's no different than what we've seen in terms of autoregulation in the regular capillary beds. You can go back to chapter 19 and it's a very similar process. If blood pressure goes down, that decreases our muscle stretch, in which case the afferent arteriole will dilate, let more blood flow into the glomerulus. That keeps GFR normal and keeps the kidneys doing their thing and doing the filtration, despite those kinds of daily little changes in our blood pressure that are kind of a normal part of the day-to-day business of our lives. So that one, this myogenic mechanism, is very similar to what we saw with the autoregulation in like a normal capillary or a non-glomerular capillary. This mechanism, this tubuloglomerular feedback mechanism, is a little different, and it's mostly a function of the macula densa. In the macula densa, they are chemoreceptors. They sense the salt concentration in the filtrate, and the salt concentration in the filtrate is actually affected by how fast the filtrate is moving. So if GFR goes up, for instance, for whatever reason that may be, that means the filtration is happening more rapidly, and the filtrate is flowing through the capsular space and through the tubules faster. That means there's less time for the salt to be reabsorbed from the filtrate, and so the concentration of the salt in the filtrate goes up. That higher salt concentration is sensed by the cells of the macula densa, and that leads the afferent arteriole to constrict, which then decreases the net filtration pressure, which then decreases GFR, decreases the flow, the rate of the flow, and allows more time for the sodium to be reabsorbed. And so that kind of gets us back to normal. The opposite would happen if you had a decreased GFR. If GFR went down, the rate of flow would go down. That means there's more time to reabsorb the salt and the sodium, so you'd end up with lower levels of sodium in the filtrate. That lower level of sodium is sensed by the macula densa. The afferent arteriole would then dilate. We'd have greater net filtration pressure, greater GFR, less time for sodium reabsorption, which brings us back into balance. So those are the two intrinsic mechanisms that keep your kidneys maintaining a pretty constant GFR. Now, extrinsically, we have both sympathetic nervous stimulation. Remember, the kidneys only receive sympathetic nervous stimulation. They don't get innervation from the parasympathetic system. When you are kind of in a kind of somewhat quote-unquote normal, right, conditions, when you're kind of just at rest, then your kidneys, the blood vessels leading to your kidneys are generally dilated, and the kidneys are getting a lot of blood flow, and what's controlling GFR are those two autoregulatory mechanisms that I just discussed. Now, if the fluid volume gets really low and the blood pressure gets really low, then the sympathetic nervous system kicks in. We get epinephrine and norepinephrine from the adrenal gland. We get increased vasomotor tone, which leads to vasoconstriction of our blood vessels. We get constriction of the afferent arteriole, which decreases GFR. The vasoconstriction pretty much immediately increases the blood pressure, and then the decreased GFR leads to less urine being made, which increases blood volume, which then increases blood pressure. And so in those instances, the sympathetic system will kick in to muck about with GFR, kind of no matter what it does to the kidneys. At that point, if blood pressure is entirely too low, it's more important that you get blood pressure back to normal. The other extrinsic hormonal control is one that we've seen before, the renin-angiotensin-aldosterone mechanism. And that is one of the main ways that we increase our blood pressure by increasing our blood volume. It's the granular cells of the JGC that release the renin. They might get told to release renin directly by the sympathetic nervous system. The granular cells might get stimulated by the macula densa if the salt concentration in the filtrate gets too low, or if the granular cells themselves don't get stretched quite as much. And so here we are looking at the renin-angiotensin-aldosterone mechanism again. When the granular cells are stimulated, they release renin. Renin helps convert angiotensin 1 to angiotensin 2 along with the ACE enzyme, and then angiotensin 2 causes aldosterone to be secreted. Aldosterone causes reabsorption by the kidney tubules of sodium. Water follows the sodium. That increases our blood volume. That increases our blood pressure. Angiotensin 2 also directly causes vasoconstriction of our arterioles. That increases our resistance, which increases our blood pressure. So that's one of the extrinsic controls. If we look at the neural mechanisms, we get the kind of activation of the sympathetic nervous system by the baroreceptors. If blood pressure gets too low, the sympathetic nervous system causes the kidneys to release renin. They also cause, the kidneys also cause the epinephrine and norepinephrine to come out of the adrenal gland. We get vasoconstriction. We get epinephrine and norepinephrine reducing the arterioles and reducing the GFR, which increases blood volume, which increases blood pressure. So these are our extrinsic mechanisms. Here's those intrinsic mechanisms, and they're really the ones that are controlling the kidneys as long as blood pressure is normal. It's only when blood pressure is abnormal that the extrinsic mechanisms take over. We have the myogenic mechanism. Decreased blood pressure leads to decreased GFR. The smooth muscle gets stretched a little less. That causes the arterioles to vasodilate. That leads to an increase in GFR. If the rate of GFR goes down, the flow of filtrate goes down. We get more time for salt to be reabsorbed. That's sensed by the macula densa, and so we get vasodilation of our arterioles, which again leads to an increase in GFR, which kind of gets us back to where we want to be. And that is really how we maintain blood pressure and how we maintain kind of proper functioning of the glomerular capillaries.